properly, then source coding and channel coding, at least fixed length of the source coding and channel coding, will be a breeze. Okay? So what is binary hypothesis testing?
Could I request the audience to come sit in front? It will make it easier for you to see.
Yeah, I mean, if you sit in front, it will make it easier for you to see. But I will try my very best to write as large as possible. Binary hypothesis testing. So this is a topic in estimation and detection theory. And as I mentioned, it is fundamental for us to understand this before we go further into lossless source coding and channel coding. So what is binary hypothesis testing? The simple case. I don't need that for the moment. Yes. So that can be pushed to the side. Okay. So in binary hypothesis testing, we have two hypotheses, which we typically call the null hypothesis and the alternative hypothesis. Okay. So in the null hypothesis, there is a random variable, but we do not know what its distribution is. Okay. So in the null hypothesis, the random variable is distributed as P, and in the alternative hypothesis, the random variable is distributed as Q. So P and Q are assumed to be different, of course, otherwise things get very boring. Okay? So there are two hypotheses that are different. So this could model the scenario where the null hypothesis is that of a signal observed without noise. A signal observed without like a DC phase, a DC component, or say a signal observed without an airplane in the sky. Whereas in the alternative hypothesis, there's an airplane in the sky plus some noise. Okay? Alright, so those are the two distinct distributions. And here, these distributions P and Q are assumed to be different, okay? And they live on some alphabet, which we call Z. So that is supposed to be a script Z, okay? So it can be assumed for all intents and purposes that the alphabet here is finite, okay? Nothing will change, but some people like to assume that the alphabets are finite to make things simpler. And our job, what is our job? Our job as the hypothesis testing person, okay, is to design a test. Our job is to design a test, which we call delta. Tests are usually called delta for some reason. Our job is to design a test. What is a test? A test is a function from the alphabet Z, much better, to 0, 1. Okay? So we would like to design this function that maps from an observation that comes either from H1 or H0 or H1 to 0, 1. Now if the test outputs 1, then we declare that H1 is the true hypothesis. And if the test outputs 0, we declare that the true hypothesis is H0. Okay? So there are two kinds of errors that we are interested in. Two kinds of errors. Okay? The first kind of error is called the probability of false alarm, okay, which we will denote by PFA. And all these probabilities of errors are parameterized by delta, the test. For different tests, for a lousy test, you have high error probabilities. For good tests, you have low error probabilities. But what is the probability of a false alarm? The way I like to think about this, and not to get things mixed up, is that H0, there's no plane in the sky, so no one is going to kill us. And H1, there is a plane in the sky, so we get bombed. Alright? So the false alarm means that, well, there is no plane in the sky, but you declare that there's a plane in the sky. Alright? So that means that the true hypothesis is there is no plane in the sky. H0. So that is a true hypothesis, but we declare that there is a plane in the sky. Okay? So this can be written as the sum of delta of Z. You declare that there is a plane in the sky, but the true distribution, the true hypothesis is H0. Okay? So that is the probability of false alarm. Okay? So another way to write that is the expectation over P of delta of Z. Okay? So another more serious error is that there is a plane in the sky that is going to kill us, but you declare that there is no plane in the sky. Okay? So all your entire army is not prepared, and your entire citizens, your citizens may be killed. So that's called the probability of misdetection. The true hypothesis is H1, there is a plane in the sky, but you declare that there is no plane in the sky, so you take 1 minus delta of Z. Okay? And this can be written as the expectation over Q of 1 minus delta of Z. That's meant to be capital. That's meant to be little. Okay? So these two are very natural performance metrics. And of course, there is also one very important performance metric that I don't really have to talk too much about. That is the complementary probability from the misdetection probability, which is called the detection probability. Okay? There is a plane in the sky, and fortunately, we detected it. Okay? So those are the three kinds of errors, I would say. Okay? And obviously, we want to design a test so that misdetection probability and the false alarm probability are both simultaneously small. But this is impossible most of the time. Okay? So what we are really looking for is a trade-off between all these error probabilities. And what we want is to in fact design a test such that all these are simultaneously small, but this is impossible. Okay? Hopefully getting a good pen is possible. Okay, so what people try to do is to look at something called the ROC, or Receiver Operating Characteristic. This is a term that is coined from the radar engineering community, right? So the receiver operating characteristic looks as follows. So people usually plot the probability of detection against the probability of false alarm. And this is the 45-degree line. These things can only be at most 1, obviously. These are probabilities, okay? And this curve usually looks like the following, okay? Now, this is known as the ROC, or Receiver Operating Characteristic, and it says what is the largest probability of detection for a fixed false alarm probability, okay? For this given test. And really, my advisor, Alan Wilsky, likes to call this point here the Holy Grail. Okay, the Holy Grail. So we want both the probability of false alarm to be small as well as the probability of misdetection to be small, or the probability of detection to be large. But this is impossible most of the time. So we can obviously, because we are interested in the false alarm and misdetection probabilities, we can flip this graph around actually, but this is not so commonly seen, all right? I'm making this up. Misdetection versus false alarm, and it looks like the following, okay? And this graph will turn out to be more useful. Okay, so we're just flipping that around because probability of detection is equal to 1 minus probability of misdetection, right? That's not so difficult. Okay, so as I mentioned, we cannot make both false alarm and misdetection simultaneously small. So we must do some trade-off. There must be a trade-off between these two quantities. And what we will be looking at is one very important quantity known as, well, there's no name, but we will give names to quantities later on. Okay, so this is known as the minimum type 2 error, minimum misdetection error probability for a fixed false alarm probability. Okay, so we're going to use this notation beta 1 minus epsilon, okay, for two probability distributions P and Q, okay, to denote the minimum, okay, the minimum, let's say the minimum of all possible tests going from the alphabet to 0, 1, of what? Of the probability of type 2 error, right? Misdetection, subject to the fact that the false alarm probability is no larger than epsilon. Okay? So because misdetections, as I mentioned, are far more costly than false alarms, we place a tolerable error probability on the false alarms and minimize over all possible tests for the one with the smallest misdetection probability. So that's exactly the expression there. Okay? Yet another way of looking at this is the following. We can minimize over all possible subsets of the alphabet Z, minimize over all possible subsets of A, minimize over all possible subsets of the alphabet Z for the following probability, Q of A complement, right? That represents the probability of misdetection, subject to the probability of false alarm being no larger than epsilon. Okay? So those are two equivalent ways of writing the same thing. Here, A, the set A, is known as the acceptance region. Acceptance region for, yes, I think I should switch the pen. For hypothesis 1. Okay? Alright, so those are some basic concepts. Can this move up? Oh, okay. This is so.
No, not that one. Vincent, just lift it up. It's just manual.
So it's mechanical.
Yes.
Oh, so heavy. Okay, so these are some basic concepts. Oh, then my pens are up there. Okay. So do you mind getting me better pens? Okay. So now we have defined a non-asymptotic quantity beta that measures the performance of a particular hypothesis test delta. Okay. So different hypothesis tests have different types of different betas, and we want to minimize this. All right. We want this to be as small as possible. We want to minimize over all possible tests. Okay. Then there is a related quantity known as the this term is not very commonly used, but I will use it anyway. Epsilon, hypothesis testing divergence. Hypothesis testing divergence. It is somewhat similar to the KL divergence, or the relative entropy, but this quantity is motivated from hypothesis testing, and it's a non-asymptotic quantity that measures the quality of a hypothesis test, very similar to beta. So it's a function of epsilon as well as P and Q. Now, in general, the further apart P and Q are, the larger this quantity, just like the regular KL divergence. And this H here represents hypothesis test. Epsilon here represents a tolerable error probability on the false alarm probability. So this is nothing but a simple monotonic transformation of the beta function. Beta divided by 1 minus epsilon. Okay, so this is nothing but a simple transform of beta. The smaller beta, the larger this is. Okay? And really, if the hypotheses are easier to be separated, you expect that beta is small for a fixed epsilon. You expect that the divergence between these two probability measures is large. Right? This is very natural. So this is minus log of the beta function up to a shift, because this is a product of two quantities within the log, and so that can be shifted, right? And then that can be written as a sum of two terms. And the second term here is a constant. It's basically log of 1 over 1 minus epsilon, which is a constant. Okay. So just a few remarks here. This behaves like relative entropy, or Kubeck-Langevin divergence, whatever you want to call it, information divergence if you wish, behaves like relative entropy. And furthermore, so what does it mean, behaves like relative entropy? So it satisfies a data processing inequality, one can show, and also satisfies, what is it called? Non-negativity. So it is non-negative for any two measures, P and Q. Think of measures as probability mass functions, okay? The non-negativity is not so easy to see. Data processing inequality is also not so easy to see. It requires a little bit of work, but it can be done. Okay? So this is one very important measure, one very important metric for us to quantify the performance of a hypothesis test delta. Okay? Now, however, this quantity DH, or epsilon hypothesis testing divergence, is a little bit hard to compute, right? Why? Because it involves an optimization. It involves an optimization over all possible regions, all possible subsets A and Z, right? Now, if your Z, if your probability measures are product measures, okay? so you observe n independent observations, then Z will be Z superscript n. Okay, Cartesian product of n different sets. Then the number of regions you have is going to be really large. And so trying to find an optimal hypothesis test may be extremely computationally intensive. So finding this quantity, evaluating this quantity of even approximating DH may be quite challenging. So we need some surrogate of DH. Okay, we need some surrogate which I call, I'm not sure who called this, maybe Hayashi, who first coined this term. This is called the epsilon information spectrum divergence. Okay, and it serves as a surrogate, as we will see, for the epsilon hypothesis testing divergence. What is this? Okay, this may be a little bit hard to parse at first, but it is quite sensible. All right. So we will use the notation D S epsilon. Okay, S stands for spectrum. Okay, S is not a number. D S epsilon P and Q. So this epsilon information spectrum divergence is a function of both probability measures as well as the permissible error probability epsilon. And what is it defined as? Supremum of some number R. Okay, this R is a real number, subject to what? So this may be a little bit hard to parse. I will draw a picture very shortly. The probability of Z, oh my gosh, Z in Z, Z in Z, such that the log likelihood ratio of P and Z less than or equal to R is less than or equal to epsilon. Okay, so is that monstrous expression? Oh, thank you very much. Okay, oh, thank you. That's very helpful. So it's this monstrous expression that we are trying to make sense of. And here's the claim, that this expression here serves as a good surrogate for the quantity of interest, which is the epsilon hypothesis testing divergence, or the beta function. Okay, and we will prove this later on, that these two are very close, in some sense. Okay, now, before we prove that these two are close, let us try to see what this means. Okay, so let us try to do a simple plot. Here is R. Okay, and here is the distribution, or rather density, if there exists, okay, of log P of Z, this capital Z, over Q of Z. Here, Z is distributed as P, as this expression suggests. Okay, so what are we after? We are after the maximum R, for which the cumulative distribution function of this random variable, okay, is no larger than, the probability that this random variable is less than or equal to this, is a particular quantity, is less than or equal to epsilon. Okay, that is a mouthful, so I'll draw a picture. I'm not explaining this very well. So here, this probability mass is epsilon, and this is 1 minus epsilon, of course. So we are looking for the maximum R, so we look at the left hand side, we go from the left, we look for the maximum R, for which the probability we collect, okay, is less than or equal to epsilon. If we go any further, we eat up more probability, so that's not permissible. Alright, so this is the sweet spot, and that's the R star, which is ds, epsilon PQ. Okay, so that's the interpretation of the information spectrum divergence. That's nice. Okay, so this is a very important quantity, and I want to mention a few remarks as to why this is cool. Why is this quantity nice, in some sense? Right? Well, as I mentioned, the hypothesis testing divergence is something very difficult to evaluate and approximate. The information spectrum divergence, on the other hand, is much easier to approximate. Why? Because it involves a probability in that. Okay, it involves a probability, and it only involves an optimization over a scalar. Alright? So if we can get a handle on the probability, then we are all set. Okay? So for example, okay, if P and Q are product probability distributions, product measures. Product measures are basically like the distributions of IID random variables, say. Product measures, i.e. P equals to product of PI, and Q equals to product of Qi, then we are in business. Because the probability contained in there, Zn in Zn, subject to log of P, let me just write. So we can easily approximate the probability. That's my point. Because if we plug P and Q into this particular expression, we see that the log of this product becomes the sum of the logarithms. Okay? Ci over Q of Ci less than or equal to R. Okay? So that is some probability. And these are, and so we can write this as in a slightly different way. Okay, log of the sum of log P of Ci divided by Q of Ci less than R. Okay, so this is a bunch of independent, at least independent, random variables. Okay, when we have a sum of independent random variables, usually they converge. I mean, appropriately normalized, they converge to something. Okay, and we can use various probability limit theorems to estimate the probability. Now, once we can estimate the probability, we can estimate the supremum. So that's my point. My point is that the epsilon hypothesis testing divergence is difficult to evaluate or approximate, so we have to use a surrogate known as the epsilon information spectrum divergence. Okay, and I have given you a small little example as to why the epsilon information spectrum divergence is easy to approximate, for product measures at least. Does this mean anything? Okay, so now, as I promised you, can this come down?
Yes.
Cannot. Oh, this is an exercise. Oh, at MIT was not like that.
Cannot be meant to be like this. What they don't do anything or should?
Okay, so as I promised you, there is a relationship between these two divergences. And I want to mention this relationship. And I want to prove at least one direction of this relationship. Okay? So, the next topic is on the relation between divergences. Basically, the above two divergences, the hypothesis testing divergence and the information spectrum divergence. Okay, and this is very classical. But the treatment today that I'm going to use is in the paper by Thoma Mitchell and Hayashi, 2012. Okay, they wrote everything in the quantum context, but it's written very well, so I understand it. So here is a small little lemma that relates these two quantities. dH epsilon, let us write it properly. For any eta between 0 and 1 minus epsilon, we can sandwich the hypothesis testing divergence in terms of the information spectrum divergence. So this is the quantity of interest. It contains the beta function, and we can sandwich this, okay, in terms of ds and dh and some quantities. Oh, there's a typo. And ds epsilon pq minus log 1 over minus epsilon. Okay, so what is the point here before we try to prove anything? So dH epsilon contains beta, which is our interest. Okay, because we want to measure the fundamental limits or the non-asymptotic limits of a binary hypothesis test. I mentioned that dH is hard to compute, and ds is much easier to compute, especially if we have product measures, which is what we are interested in. So here I provide a couple of bounds for ds, for dH in terms of ds, the information spectrum divergence. And what do we see? We see that dH is very close to ds, and we can toggle between the two. If we take epsilon, or if we take eta here to be much smaller than epsilon, this is essentially ds, okay? Because you can believe that ds is continuous in epsilon, which is not true, okay? So, but this is close to ds epsilon. And the lower bound also suggests that dh is also close to ds, because this basically, all these things are constants. You can think of them as constants, okay? So, well, the agenda then is to focus on dh by evaluating ds on the left and on the right, and sandwiching dh in terms of ds and sandwiching dh in terms of ds and ds here, and choosing eta appropriately. Now note that we really need epsilon to be less than 1, otherwise we cannot find such an eta. Okay? So now let us try to understand this statement a little bit better, okay, by proving at least the lower bound. Okay? Okay, so what is the meaning of dh? Well, dh is basically up to a constant, up to some simple transformation, this beta function which has been erased, I guess. Beta is the minimum over all possible regions of the misdetection probability subject to the false alarm probability being no larger than epsilon.
Vincent, beta is there. Beta is the unerased.
Oh, thanks. Good. It's unerased at this point. So that was good planning. Okay, so let us at least try to prove the lower bound. And as we will see, the lower bound corresponds to an achievability. The upper bound is slightly more involved, corresponds to a converse, which we will not do. So, in the lower bound, what we are after, what we want to do is to propose a test that satisfies some properties. Okay? Then we can prove the lower bound. Because beta is basically an optimization over a bunch of things, either a function or a region, right? So we just have to propose a test in order to prove this lower bound. So what is the test? What is the most natural test in a hypothesis testing problem? From the Neyman-Pearson lemma, we know that we should really look at the likelihood ratio, right? Neyman-Pearson lemma says that we have to look at the likelihood ratio when we perform simple binary hypothesis tests. So propose a test, the test delta. What is the test we will propose? Delta of z, taking on the value 1 if the following is true. The logarithm of p of z divided by q of z is less than or equal to gamma. Okay, so this is this indicator function. It says that the test should output 1 if the likelihood of p is smaller than the likelihood of q up to some threshold. Okay, so we will choose gamma carefully, and we will choose gamma in fact to be a function of the spectrum divergence. We will choose it to be ds pq minus say alpha small, and alpha positive. Okay, so we will choose gamma to be a slight back off from the epsilon information spectrum divergence. So this is the test, okay, and this is very natural, okay, right. So why this direction? Well, remember that we really want to output 1 if and only if we believe that the hypothesis is H1. H1 corresponds to Q. So you want the likelihood of Q to be large, right? So if you move this over here, the likelihood of Q is larger than that of P. So this sign looks sensible, right? So the likelihood of P is small. Okay, so let us try to analyze this test, which is not so difficult. So let's look at the expectation value of P, delta Z. Okay, this is nothing but the probability that the log likelihood ratio, Z distributed as P, QZ is less than or equal to ds epsilon minus alpha. I dropped the arguments. It's ds pq. Okay. Now, by the definition, so alpha is something very small. Okay. Alpha is something very small. So if we look at the definition of the information spectrum divergence, okay, and we look at the information spectrum divergence evaluated at some point slightly smaller than ds epsilon. All right. The probability mass that we collect is less than epsilon. right? If we move slightly to the left of R star, the probability mass we collect is slightly less than epsilon. So this is less than epsilon, by the definition of the information spectrum divergence. Okay, so we satisfy the false alarm constraint. Right? We satisfy the false alarm constraint, which is exactly expectation value of P delta Z, this part here. So this is a legitimate test, the way we design the threshold gamma. Okay? Now then let us evaluate the false, what is the other probability? The misdetection probability. Where is that? Okay, the misdetection probability can be written as expectation value over Q of 1 minus delta of Z. Now this requires some simple calculations, really simple calculations. And so what is the meaning of expectation? Well, the meaning of expectation we should know from a simple probability class. You basically put the probability measured where it's supposed to be, and you put the function, which is the indicator, log PZ over QZ greater than gamma now. Right? Because 1 minus, we basically flip the test. Okay? So that is the expression that we are after. Okay, great. What are we after now? So here we observe that Q of Z, for every Z in here that is active, alright, Q of Z is less than P of Z, 2 to the minus gamma, right? So we have Q of Z, P of Z, P of Z, 2 to the minus gamma, because
Inequality.
inequality, thank you. It can be strict, no problem, okay? 2 to the minus gamma of 1 log of P of Z, Q of Z greater than gamma. So we are just making use of the indicator condition, right? So now you can upper bound the indicator function, no problem, by 1. Okay, and the summation over all probability mass elements, the entire probability mass function is 1. So this reduces to 2 to the minus gamma. Right? This is some simple calculation. And so the misdetection probability is upper bounded by 2 to the minus what? ds epsilon pq minus alpha. Okay? So by some simple rearrangement and the definition of the hypothesis testing divergence, we observe that this inequality can be established quite easily. Okay, in particular, the divergence, the hypothesis testing divergence, is nothing but a monotonic function of the beta, of the minimum type 2 error given the false alarm error is no larger than epsilon. So we just simply have to take the logarithm and subtract some appropriate constants and let alpha tend to 0. Okay, so that basically proves the lower bound. So are there any questions? So that bound there is everything we need in order to study the fixed error asymptotics of hypothesis testing. Are there any questions?
Since you assume that the Z is finite.
We don't need Z to be finite, not a problem.
I understand, but you assume Z to be finite.
Yeah, we don't need it.
You could replace all these groups by maxes and get rid of alpha to begin with. You could have
Yes.
zero.
We do not need Z to be finite, but I want to write sums.
Okay.
Because integrals scare some people.
No, that's fine. No, what I was trying to say was the following. You could have get rid of alpha to begin with.
Yes,
Since all
we
your
can.
groups are maxes, you
Yes,
could have alpha is equal
we
to 0.
could in fact get rid of the alphas.
Right.
Yes. Okay. Okay, so now I want to talk a lot about asymptotic expansions. Okay? And this will be the subject of the next half an hour before we go to the break. Okay, so what is the meaning of asymptotic expansions? What are we after? Okay? So here, asymptotic expansions for dH and ds. Okay? So what are we after? Now, we will consider the situation where we replace P by the product distribution, a product distribution. Now, the components of the product distribution do not have to be the same. Alright? So here we will assume that P is that quantity, the probability measure, the product probability measure, whatever, okay? And we will also assume that Q is replaced by Qi, the product of Qi. And we will assume that N is very large. And we will then understand what are the asymptotic expansions for ds and dh. So that's the setup. Okay? These do not have to be the same. The component distributions do not have to be the same, and that's important for channel coding. So, okay. So before we talk about asymptotic expansions, I want to remind you of some fundamental quantities that you might have seen before. Now, for two probability distributions, we define the relative entropy finite sets. Okay? PQ, PI, QI, by the average of the likelihood ratio. This is very natural. This is the average according to P of the likelihood ratio, right? So that is the relative entropy, Kullback-Leibler divergence, information divergence, whatever you want to call it. Okay, and perhaps what is not so familiar is the variance. Okay, this is called the relative entropy variance. Okay, VPIQI. Right. So the notations are very similar, and the definitions are also very similar. This is a variance of this particular random variable, log of pi over qi. Well, what is the meaning of variance? We basically look at the second, the centralized second moment, right? So we have to subtract the mean, and we take the square. So that is something known as a relative entropy variance, right? So these two quantities will come out to be very useful in our evaluation of the asymptotics of ds and dh. Okay, so with these out of the way, here's an exercise. We can try to evaluate the asymptotics of ds first. Okay? Because ds it involves a probability, so things become slightly easier. Okay? And this is what we have. Okay? So let us assume that the infimum over all possible component distributions of the relative entropy variances are greater than 0. So all of them are bounded away from 0. Okay? So we cannot get arbitrarily close to 0. Okay? And epsilon is between epsilon is between 0 and 1. I will not state that. Then we have the following: ds epsilon of Pn Qn is equal to, so that's an asymptotic expansion. I haven't defined what's Pn and Qn, but it's basically the product distribution, as I mentioned above. Similarly for Q. ds Pn and Qn is given by n of dn plus square root n Vn V inverse epsilon plus O1 plus and most a constant term. Okay? So this is somewhat reminiscent of channel coding already. So we are taking one step towards channel coding. Of course, there are many more steps. But there are many things here that are undefined, in particular D and V. And Dn is basically the average of the divergences up to n. And Vn is basically the average of the relative entropy variances up to n. Okay? So we have an asymptotic expansion. This is the first experience that some of you might have had with evaluating this fixed error probability asymptotics. Okay? At least for ds. So a simple corollary, which I will not state but is in the notes, in the slides that I have provided, is that if all these component distributions are the same, then obviously the average reduces to one divergence. The variance here reduces, the average of the relative entropy variances reduces to one of the variances, end of story, right? So that's simple. Okay, so let us try to justify this a little bit. Okay, let's try to provide at least a proof sketch. Okay, and I deliberately left this on the board because we need the definition of the epsilon information spectrum divergence. Okay. So is there any question on the the statement. Okay, so these P and these Q's are basically product distributions, and these are the asymptotic expansions, and we need a small little technical condition. Okay, we also need some other technical condition that I have not stated, but it's okay. I just want to convey the big idea. Okay, so that's great. So let's try to provide a small little justification, a short justification. Okay, so for this we need to recall some basic facts from probability. Okay, so can we recall what is the, now let us try to recall what is the central limit theorem. That will come out to be useful. Central limit theorem. Now you must have heard of this in your before, but let me just remind you of the way that we are going to use it. Now let a bunch of x's be independent. Let xi's be independent random variables. Let this go up to infinity. Okay. Let this be independent random variables with some finite variance. Let me just state it in this particular way. Say expectation of xi is equal to 0, expectation of xi squared is equal to sigma I squared less than infinity, and the third moment here is also finite. Absolute third moment is also finite. Okay? Then we probably don't need some of these conditions, but all these conditions will come in handy when we state the Berry-Essien theorem, which is a generalization, quantification of this. Okay, so 1 over square root of n, sum of these random variables. So that is some normalized root n normalized version of the random variables. Okay, if we take the probability and we consider a cumulative distribution function, okay, this converges for every a to the Gaussian cumulative distribution function. Okay, that is the meaning of central limit theorem, right?
There's some sigmas that are missing.
There are some sigmas that are missing. Okay, there are some sigmas, there's a sigma here, right? And sigma here, sigma squared is defined as the average of the sigmas. Okay. So that is basically the probability that a Gaussian random variable, this is normal 0, 1, is less than or equal to a. Okay. So that is the central limit theorem. Okay, so what we need is something slightly stronger than the central limit theorem, known as the Berry-Essien theorem. Actually, we do not need that from the second order asymptotic viewpoint, but it will be good to know this anyway. Okay. So as you can see, what this means is that, what the central limit theorem tells us is that this normalized bunch of random variables converges in distribution to a Gaussian. Converges in distributions to a Gaussian. Okay. So what we really need, if we want to establish the O1 term, that's the O1 term, the remainder O1 term there, is something known as the Berry-Essien theorem. Okay. Okay. So assume the same conditions as above. Assume the same conditions as above. What we have then is a uniform version of the central limit theorem. Supremum over all possible points of evaluation A of what? Of the probability that 1 over sigma root n sum of xi less than a minus the Gaussian version is less than let's say 6t divided by root n sigma cubed. Here t is equal to the sum of the third moment. And actually this is nice because this holds for every n. Okay, this is quite nice. This holds for every n. So this is quantification of the rate of convergence in the central limit theorem, right? This is a quantification. It says that this probability and that probability differ by at most O1 over root n, okay, for every a, okay, independent of the a you choose. That's quite nice. Okay, so that's very nice. So now what we can do, what is our agenda? Our agenda is to prove that little theorem over on the top left-hand corner. Okay, and what do we have to do? All right, what do we have to do to prove that? Well, we basically need to evaluate the information spectrum divergence, right? We basically need to evaluate this information spectrum divergence when the probability measures are these independent ones, these membreless, stationary membreless distributions, those things there. Okay? So we have tools. We have probability limit theorems now, the Berry-Essing theorem, the central limit theorem. Let us try to use the Berry-Essing theorem. Okay? Let us try to evaluate the probability contained in the epsilon information spectrum divergence, and let us try to evaluate. Let's try to do that. So I will try to estimate. I will try to estimate the probability. So this is the probability in the epsilon information spectrum divergence. Okay, that can be written as the probability when we use PR. We have to be very clear what the distribution of the random variables contained therein are, but we can be clear. Log of P of n, Z of n, divided by Q of n, Z of n, less than R. Okay, but these two are product measures, right? So this is separable into a bunch of independent terms. Okay, so that is probability of the sum, log of Pi Zi, Qi Zi, less than R, no larger than R. Okay, right? So that is very convenient. That is something very convenient property of the information spectrum divergence. You need to concern yourself with probabilities. So now we have a bunch of independent random variables, right? These Z's are distributed according to P. So the averages of these things, okay, are exactly up to a scaling factor Dn. The variances of these independent random variables are up to some scaling factor Vn, right? So what we can do is to simply appeal to the Berry-Essing theorem here. The third moment must be finite, okay? We shall not talk about, okay? So what we can do now is to appeal to the Berry-Essing theorem to estimate this object. And by some simple normalization, by some normalization factors, we can see that this is exactly phi of, correct me if I'm wrong, R minus n dn divided by square root of n vn. So we basically need to normalize these random variables so that they have they have zero mean and some appropriate variance, which I've done so here, plus a term that is 1 over square root of n. Everything, all these things can be collapsed into the old notation. Say everything is finite. And the condition that the infimum of the relative entropy variances be greater than 0 is to ensure that this sigma here doesn't become too small. Okay, so we have this estimate for the probability of error, the probability contained in the information spectrum divergence. We equate that to be epsilon, or we take that to be less than or equal to epsilon, and we solve for the optimum R. As I mentioned, we need to solve for the R such that the left-hand side contains probability mass at most epsilon. So we equate, roughly speaking, we equate this to be epsilon, we solve for the optimum R, and voila, we get the answer, right? If we rearrange this equation slightly, we get that expansion there. So we move this O term over, this is small, we take the inverse of the phi function, we multiply by n Vn, and we move the n dn over. So these are some simple calculations that I will not do. Okay. So as you can see, the evaluation of the epsilon information spectrum divergence turns out to be quite straightforward. Okay. Now, once we have the relation between the divergences, we can then provide quick and easy means. We can now provide a quick and easy means to evaluate the what is the other divergence? The hypothesis testing divergence, right? Because we have this relation between dH and ds, which unfortunately has been erased due to my poor planning. Okay. So recall that dH and ds are very close, and dH is exactly what we are after in a hypothesis test because it contains the beta function, right? So our real objective is to find an asymptotic expansion for the minimum misdetection error probability for the false alarm probability being less than epsilon. That's beta. Okay. So let us try to then one page missing. Okay, no. Let us then try to understand yet another result that will turn out to be very, very useful. Okay? Our real objective is to get a handle on beta when the distributions contained therein are product measures. Okay? Not necessarily the same in each component. This will turn out to be useful in channel coding. So what we are after is in fact an asymptotic expansion of the form Pn Qn. Right? So here I don't think I use this notation, comma. Alright? So here the component distributions are product distributions, not necessarily the same in each component. We want to understand this expansion. Okay? But we have a relationship between dH and ds as well as dH and this beta function through some simple formulas. Okay? Here's the claim. This is at most, this is equal to n dn. All these notations have been defined. Plus root n Vn phi inverse epsilon plus at most O log n. This thing can be optimized, okay, and it's half log n. Okay, this thing can be optimized, but we will not do that. We will not do the optimization of the third order term today. So this is another result that will turn out to be very, very useful, especially for source coding. We will see that this will exactly lead to the asymptotics for source coding, fixed to fixed length lossless source coding. Okay, and really the proof is trivial. The proof from now on is really trivial. Okay, and basically we have some relations between the dH and ds as well as beta and dH. Okay, so let me just say that the lower bound follows by asymptotic expansion for ds. Okay? Because dH is exactly lower bounded by ds up to some constant. The constant can be absorbed into O log n. Right? dH is lower bounded by ds with the same epsilons up to some constant, which can be absorbed into O log n. Okay? Now, so we only have to concern ourselves with the upper bound, which involves only one technique. Okay? So recall that dH epsilon is upper bounded by ds epsilon plus eta up to some, what was that? Log of 1 minus eta, 1 minus epsilon over eta. Something like that. Okay? Where I have dropped the dependence on the distributions since they are all the same. So, we have some expansion for ds. We would like to get a handle on dH. Okay? Which will provide us with some handle on beta. Okay? So what we have to do now is to look at what is the eta we should choose. Recall that eta must be chosen to be less than 1 minus epsilon. Right? I mentioned that eta must be some number between 0 and 1 minus epsilon in the lemma relating the divergences. Right? So, the appropriate choice is eta equals to 1 over root n. Okay? So we take these constants to be dependent on the block length. Okay, as we'll see, we can take these constants to be anything we want because all these are, the relationship between the divergences is a finite length result. Okay, it holds for block length 1, it of course holds for block length 100. So an appropriate choice is this. And let us try to now evaluate dH epsilon, an upper bound for that. And that would directly lead to a lower bound for this. Qn, okay, this is upper bounded by ds epsilon plus 1 over a root n, right? And exactly the same things, plus log, you have a log 1 over eta. You have a log 1 over eta here, right? And log 1 minus epsilon is constant. So I think this will turn out to be half log n. That's where the half log n comes about in the converse, or in the upper bound of the dH plus 1. Okay? But, hey, we have an asymptotic expansion for ds epsilon, right? And the asymptotic expansion for ds epsilon is over there. Alright? So, we can simply copy down the asymptotic expansion, dn plus root n vn phi inverse. Now the epsilon is replaced by epsilon plus 1 over root n. Now there are some technical things here that I've swept under the rug, okay, because that's already asymptotic. But we can do that, trust me. Okay, plus all these stuff here, which I will collect into O log n because I do not want to write so much. Okay? Aha! So we are almost done, right? Except for this epsilon plus 1 over root n. Now, phi inverse is some function. And in fact, it is differentiable. So we can take a Taylor expansion of this at epsilon. Okay? And what we get is, let me just use a different color. This is roughly phi inverse at epsilon plus order of 1 over root n by Taylor expansion because it's smooth. So because Vn is lower bounded by some quantity, okay, because all the component relative entropy variances are positive, so we can continue this chain here. Vn plus root n, Vn, phi inverse epsilon. This n and this n cancel, it gets to an O1 term, and we get exactly O log n. So we have proved this little result. Note that log beta 1 minus epsilon is roughly dh, okay, up to some constant which we can absorb into the asymptotic O terms. So what do we have? Let me just summarize before we take a break. We have 8 minutes more before a break. See, I'm getting better at this. Okay, let us try to summarize our results. Then we will take a break and we will next talk about lossless source coding. Lossless source coding, if you understand everything I've talked about right now, lossless source coding will take 10 minutes. Okay, so we have an expansion for beta 1 minus epsilon, log of 1 minus beta epsilon, and it's given as follows. Now, as I mentioned, a simple corollary is the following. If all the PIs are the same as P, and all the QIs are the same as Q, and these are different, P is absolutely continuous with respect to Q, and this is the condition we need, but I will not state these things. Okay, for all I, then minus log of beta 1 minus epsilon, Pn, Qn, right, is equal to n divergence plus root n relative entropy variance plus O log n. And what does this remind you of? Okay, we have actually derived something slightly stronger than the Chernoff-Stein lemma, which you can find in chapter 11 of Kover and Thomas. Okay, so this corollary is a slight strengthening of Chernoff-Stein. Chernoff-Stein states that, chapter 11, this is something I teach. Chernoff-Stein lemma states that if epsilon is between 0 and 1, I will not state that, the normalized logarithm of the optimum misdetection error probability when we have product distributions converges to dpq. So we have in fact strengthened this. We've in fact strengthened this little result by Chernoff-Stein in the fact that we have, oh, something is missing here. Very important. Okay, so we have in fact strengthened Chernoff-Stein because we have derived this remainder term here, which is quite nice because Chernoff-Stein, if you look at Chernoff-Stein lemma, it does not, the limit does not depend on epsilon. Whereas what we have done is to refine it such that the asymptotic expansion reflects the dependence of this quantity on epsilon. So that's nice. Okay? So here is where I want to take a short break, and please return after 15 minutes. And the next part of the talk will be on lossless source coding and channel coding for discrete sources and channels. Okay? So thank you very much for your attention.